So I think we can start. So the plan for today is, okay, in the morning we are going to continue the composite materials. I hope to close the composites by the end of the morning lecture. And then in the afternoon, we are going to start the transverse shear. Okay? And then in the computer lab, after, we are going today to do one example that involves contact and interaction, which is something you will need for your assignment. So we will spend the entire computer lab today on that example. So it takes some time to do that example, and I want you to do it yourself. So I will upload the example, the tutorial, soon during the breaks between the lectures. I will upload in Brightspace. But that is the plan for today. So let me start the composites just by doing a very quick summary of what we did last week. Okay, so last week we started with on-axis properties. So basically we defined a lamina or a ply having this orientation of the fibers. This one's in green. Okay, so this is the axis XY. So X, the direction of the fibers. Y is the transverse direction. And we obtained a relation between the strains and stresses. So that relation was given by this compliance matrix, remember? Okay, so let me so this is what we did last week. And of course, this matrix will multiply the stresses. So this is a relation for a lamina with this particular configuration, very well aligned so the fibers aligned with the x-axis. So we call this matrix as the compliance matrix, okay? Basically as the properties that relates so given a stress field, we can get the strain field by just multiplying the stress with this compliance matrix. If we want to get the stresses from the strains, we need to invert this compliance matrix, and then we end up having the stiffness matrix, which is this matrix. I'm going to put it here now. Okay, so you have here So this is many times written like this. Okay. And then here on the right-hand side, of course, we have the strains. So these terms here you have, so Q11 is X. So if you just invert the compliance matrix, you obtain this. So I'm just putting here the final equations here. So of course, you can find these relations in the books that were recommended for this model, but I'm just putting here everything in case you want just to follow. Okay, and all the others we are going to consider equal to 0. All right, so this matrix is many times represented like this, and this is the stiffness matrix. Okay, which allow us to obtain the stress field from a given strain field that is imposed on the composite. So we did this last week. We then moved to the off-axis properties of the lamina. Okay, so basically what we did also last week was we did some revision on stress transformations, remember? So if we have now a lamina or a ply with this generic orientation of the fibers, so this angle, I think it was given like theta last week. Okay, so this is the global axis, xy, and I think I defined last week this axis x bar and y bar, right? And then what we did last week, so we talked about Mohr circle, remember? We talked about all of that. And we concluded that in order to get my stresses in this x bar, y bar coordinate axis, so this is the stresses I'm looking for. This one's in green in this coordinate system. What we concluded was this can be obtained from this transformation matrix, cosine square of theta, sine square, 2 times sine cosine, cosine square minus 2 times sine cosine minus sine cosine here, sine cosine, and then here cosine square minus sine square. Okay? So we call this transformation matrix T. And then what I have to do is I have to multiply this transformation matrix with the stress field in the global coordinate system, okay? We can say this is the global coordinate system. The one in red. So this transformation matrix allows me to transform my stress tensor from one coordinate system to another. So this is stress transformation that you did learn in your year 2. Nothing special. Of course, if we want to do the other way around, if I want to get the stresses in the global coordinate system, come on, from the stresses in the local coordinate system, our sigma bar, sigma x bar, sigma y bar, tau x y bar. What I need to do on this transformation matrix T, I need to invert this matrix. So what I will have here will have to be the transformation matrix inverted. Okay? And that transformation matrix, if you do the inversion, you get this coefficients of sines and cosines and square. Okay. Of course, we can just memorize this transformation matrix and the inverse of the transformation matrix to transform the stresses from one coordinate system to another. That is not a problem. I think the most important thing here is for you to understand what is going on here. So why do we need to do the transformation? For example, if you look at this lamina here, why do I need to do this transformation? Well, I need to do the transformation, for example, think like this. My loading is going to be applied in my global coordinate system, the one in red, right? Either I apply a strain or I stretch. Imagine I stretch this lamina in the x direction. So imagine that I do this. If I stretch the lamina in the x direction, of course I'm exaggerating here. Imagine I'm imposing a strain in the x direction, right? So I want to know what is the stress that results from this stretch. But the stress along the fiber direction in the green axis, sigma x bar. Because then I can say, okay, my fibers are able to carry this stretching. You know what I mean? So we are going to see a failure criteria for composites, the Tsai-Hill criteria, which we have to do exactly something like this. We have to transform, we need to get the stress tensor in this local coordinate system of the lamina. this x bar, y bar, so then we can assess if this ply is going to fail or not when I apply a loading in the global coordinate system, because usually we apply a load in the global coordinate system, right? For example, imagine if you have a laminate with 5 laminas or 5 plies, all with different orientations. We always apply a load in the global coordinate system, right? But because the plies have different orientations, we need to do this stress transformation for the different orientations of the plies, and then we need to go and see, okay, for every single ply we have in our laminate, if there is one that fails, it will compromise the entire laminate, right? So we will do that. But my point here is just for you to try to understand why we need to do these stress and strain transformations. What's the reason for it? And I give you this example. I hope. Just one more thing here before we move on. So let me copy this. No, not this. Let me copy this one to a new slide. So this is the transformation for the stresses, right? If I want to do a transformation for the strains, the transformation matrix is going to be exactly the same as the one you have here. The only thing that will change is here, instead of the stresses, you will have the strains. And here you have 1 over 2 gamma x y. All right? That's the only thing we need to keep in mind, is that instead of gamma xy, we have 1 over 2. So here we will have deformation in the x direction, in the y direction, and 1 over 2 gamma xy, the shear strain. Okay? So that's the only thing we need to take into account. Now let me, so what I was saying in that example, we apply a load in the global coordinate system, then we need to transform. So I'm going to put it here in some more specific terms. So if we apply some strain in the global coordinate system, okay? So the first step I have to do is I need to do a stress-strain transformation and convert this strain field to the local coordinate system. So I need to multiply this by my transformation matrix. Okay, this is my transformation matrix. And then if I do that, what I obtain is my strains in the laminar coordinate system. Okay, so you might notice there's the 1 over 2 is not here, is missing here. That's why you have this 2 here, just to compensate for that. So we obtained the strain field in the laminar coordinate system, this one in green. the next step, what I have to do is, now that I have my strain field in this coordinate system here, let me copy this to there. Maybe it's easier. Now that I have my strains in these directions here, X bar and Y bar, what I'm going to do is, if I multiply this strain field by my stiffness matrix, right? If I do this, if I multiply this by my stiffness matrix, which includes those terms I defined, so I'm just going to show you. So these are the terms I introduced here, okay? These terms here, this, and this, right? The terms of my stiffness matrix. So if I do this, what I obtain is the stress field, right? So what I will obtain here is going to be my stress field sigma x bar, sigma y bar, tau x bar, y bar. Right? So, we can say this is the first step. First step, which is from a given strain in the global coordinate system, I do just strain transformation to get the strain in the laminar coordinate system, the one in green. Once I have the strain in the laminar coordinate system, I multiply it by the stiffness matrix of the lamina to obtain my stress in the local coordinate system. So this is my second step. Okay? My third step now is going to be what? So this is, let me get rid of this to get some space. Now that I have my stress in the local laminar coordinate system, if I apply so let me just put here, so this is our transformation matrix, C. If I apply now the inverse of my transformation matrix, I will be able to get my stress tensor in the global coordinate system. Okay, and this, I'm going to comment on this. So this inverse matrix, I already show you, is the inverse of the transformation matrix. Okay, so this matrix is C minus 1. Which is the same thing as C transposed. Okay? So this is going to be our third step. Okay, let me see if I can make this smaller. so it fits all in one page. Okay. Now, let's discuss a little bit one important thing here. So you are used to do this process for an isotropic material that is not a composite material. You are used to do this in one step, right? So that step is, if I give you the strain tensor in the global coordinate system, you just use the Hooke's law, right, to get the stress tensor, right, stress field. But here in composites, we have to do this in these 3 steps. The reason is because exactly the orientation of the fiber and the different properties of the lamina, or the properties of the lamina, they change with the direction, right? Which is not the case for an isotropic material. Isotropic material, so the iso thing on the isotropic means equal. Yeah, equal in all directions. The material properties are the same in isotropic material, right? But it's not the case for a lamina, for a ply. So we always have to do this transformation first to get the stress or strain in the lamina coordinate system. Then we apply the stiffness matrix of the lamina to get the stress in the lamina coordinate system. And then we need to transform back to get the stress field in the global coordinate system. So these 3 steps is what we are going to do. And I think nothing better than do one example. What do you think? Let's do one example so we can see these things working in practice. So the example I have, so basically is a pressure vessel. So we have a pressure vessel like this. So let me see if I can draw it more or less properly. Okay, we have a pressure vessel like this. And, okay, this is the mid-surface. So we have the fibers oriented like this in the pressure vessel, okay? So this angle from the horizontal axis to the fiber direction is alpha, unknown, right? So let me see what is given in the question. Okay, the diameter, this distance from here to here, is 2 times the radius, of course, is diameter. So this is equal to, well, it's not given any numerical value, so let's use R. 2R is diameter. So the question is, they want to know optimum orientation alpha of the fibers. Okay, such that fibers are subject to tensile stress with no transverse or shear stresses. Okay? So, imagine you are working in a company, manufactures pressure vessels made of composite materials, and you have to define this orientation alpha. Okay? What is the optimum orientation alpha? You remember that I told you last week that this composite is, this lamina is very strong in this direction. Okay, very strong. But in this direction is very weak. Right? So the optimum means all the load is being carried in the direction of the fibers. If we have any load being carried on the transverse direction to the fibers, because that is very weak, right? Probably it will fail, right? So the optimum orientation is to, okay, what is the orientation that will allow my loading to be on this direction of the fibers? In fact, in the question, is already telling you how to obtain this optimum by just imposing no transverse shear or direct stresses to the fibers, right? So let me just see if there's any other information. No, there is not. So what we are going to do is, so we know this is a pressure vessel. So this is the information you have. So you have, of course, you have some gas inside with some pressure. Okay, let me write here gas inside with pressure P, generic pressure P. So we need to know for this for this pressure in the pressure vessel, what is going to be our loading? Well, just very quickly. So if you have a pressure vessel like this, okay, if you look at an element here on the pressure vessel, it will have, so if this is my x direction, y direction, global directions, so it will have a sigma xx, because you have pressure inside, so the pressure is hitting these walls here, and then is producing a sigma xx stress, right? But also what is happening is the pressure is also hitting these walls here in the radial direction. So, and because of that, you will have a sigma yy. Okay? Does it make any sense or not? You did pressure vessels in year 2, or you didn't know how to obtain these stresses? Okay. So we might need to do something quickly here, hopefully. All right, so let me think like this. Let's look at sigma xx first. So what is going to happen? Okay, you will have something like this, sigma xx So what I'm doing here is I am looking at this. I'm looking at this thing here. I'm looking from this side. Okay, imagine I am inside the pressure vessel and I'm looking to that spherical, semi-spherical thing, and then we are going to have the pressure here. Right? And then this pressure will be in equilibrium with this sigma xx. And then if, okay, this is going to be my x direction, right? If I do the equilibrium of the forces in the x direction equal to 0, so I have the force produced by the pressure, so that will be the pressure, times the area. The area is pi times the radius square. This is the area where the pressure is being applied, right? Okay, don't forget this distance from here to here is the radius, which is equal to this, right? Radius, okay? And then I have, in the opposite direction, I have my sigma xx, which is a stress, so I need to multiply by an area. And that area is going to be, so if I look now from the top, I will get something like this. Okay? This is the area. So this is equal to the thickness of the wall, T. Okay? This is radius. So my area is going to be equal to 2 times pi r, which is the perimeter, times the thickness. Area, okay, area of the stress, where the stress is applied, this is the area where the pressure is applied, right? Okay, this is a bit out. I was not planning to do this here today, but anyway, I found out you didn't do this in year 2, so it's better to spend some time. So, and that's all the forces we have. So for this free body diagram, so this is my free body diagram, right? Remember from year 1? This needs to be equal to 0 to be in equilibrium. So pi cancels out. And then we have the square cancels out with this r. So we have pressure times the radius over 2t is going to be equal to sigma xx. Okay? You see, just a very, this came exactly from what we did in year 1, statics, yeah? Summation of forces in this direction x equal to 0. I have a free body diagram here with all the loads applied there. I just do the summation of forces in the y direction, and from this equilibrium equation, I get the value of my stress, sigma x. So this one, sigma y, you can do at home. I will give you the final result, which is pressure times the radius over t. This is homework. I cannot afford to spend more time on this. Sorry. We need to move on. Okay. Now that we know sigma xx and sigma yy, what I'm going to do is I'm going to apply the stress transformation, equations for stress transformation. So I'm going to say, so coming back here, so this is going, let me just put the axis here. So this is going to be my x bar. And this is going to be my y bar. Okay? And my global axes are this, x and y in red, okay? So I'm going now to transform. So what we have sigma xx, sigma yy in red. I'm going to transform from the red coordinate system to the green coordinate system, or to the laminar coordinate system, x bar, y bar. So I'm going to write so sigma x bar, So I can use that transformation matrix, or I can use this sorry. Let me do the other way around, I think it's better. So we will have sigma xx on the left-hand side equal to the sigma x bar plus sigma y bar. So all of this is stress transformation, okay? So you need to master very well stress transformation to be successful in composites. It's nothing more than this, basically. It's all about transforming from one coordinate system to another. Okay. Sigma yy is going to be equal to this. Now here we have not cosine of 2 alpha, but cosine of 290 minus alpha. Let me just move this a bit there. Same thing here. 290 minus alpha. Okay. So these are the stress transformations. Allows me to transform, in this case, from the laminar coordinate system, the one in green, to the global coordinate system, the one in red. And why am I putting this on this way? Because the next step is quite obvious. So I can even do something more here, because we know sigma xx is equal to pressure times the radius over 2t, and this is equal to pressure times the radius over t. Okay? So what I was saying is that the reason why I'm putting this way is because now I'm going to do this. No transverse or shear stress in the laminar coordinate system, right? I don't want this lamina to be carrying any stress in the perpendicular direction to the fibers. So that basically is saying in these equations sigma yy equal to 0, tau xy equal to 0. I'm going to impose this to say, if I say this, so the only stress that my lamina is going to be carrying is sigma x bar. And then my equations become much, much easier. So if I continue here, I will get pressure radius over the thickness is going to be equal to sigma x bar over 2 plus sigma x bar over 2 cosine of 2 alpha. That's it. And then below, the second equation is here is 2t, PR over t equal to sigma x bar over 2. And now I have cosine of 2 times 90 minus alpha is going to be equal to minus cosine of 2 alpha. So I get this. Okay? Or I can do even better. I can say this is going to be equal to sigma. I can factorize sigma. And then I will get 1 plus cosine 2 alpha. And here I will get sigma x bar 1 minus cosine 2 alpha. Now, if I divide these two equations, if I divide the left-hand side, if I divide this by this, I will get 1 over 2. And on the right-hand side, this cancels with this if I divide both, right? I will get 1 plus cosine 2 alpha over 1 minus cosine 2 alpha. Right? Look, the only variable I have in this equation is alpha. I can say this is going to be 1 over 2 minus 1 over 2 cosine 2 alpha is going to be equal to 1 plus cosine 2 alpha. So basically, I will have minus 1 over 2 is going to be equal to 3 over 2 cosine 2 alpha, right? Or if you want, I will have so I will have minus 1 equal to 3 cosine of 2 alpha. So that will give me cosine of 2 alpha equal to minus 1 over 3, which, yeah, did I make something wrong? Yeah.
What happened to the 90 minus alpha that was in the bracket of the question?
This one here?
Yeah.
I just put, so cosine of 180 minus 2 alpha is equal to minus cosine of 2 alpha. Okay, let's look at the trigonometric. So you have something like this, right? Trigonometric circle, right? So this is my 2 alpha angle. And this is my okay. Yeah, this is so this angle here. So if this is 2 alpha, this angle here is going to be 180 minus 2 alpha. Because we had cosine of 2 times 90 minus alpha, right? This is same as cosine of 180 minus 2 alpha, okay? Which is this angle here. So the cosine of this angle in red is this bit here. So this is cosine of 2 times 90 minus alpha, which is equal to, minus cosine of 2 alpha, right? Trigonometry, isn't it? I'm a bit rusty with that, but I think so. Basically, I replaced cosine of 2 times 90 minus alpha with minus cosine 2 alpha. That's what you have here. Sorry. So this step, let me see, this step from here to here, you can see the minus there, right? Okay? All right, so according to my calculations here, so 2 alpha is going to, sorry? How much is that? Yeah. You mean this minus here? Because cosine of this angle will be a negative number, right? Cosine of this angle in red, is this bit here, right? Is on the negative side. Sorry?
Because why not the red color one is negative?
Because I replaced this, I want to replace this argument here with 2 alpha, right? Because that's what I have here, is 2 alpha, right? 2 alpha. And I cannot say this is equal to cosine of 2 alpha because it's not. It's equal to minus cosine of 2 alpha. Because 2 alpha is this angle here in green, and the cosine is in the positive side, isn't it? So I cannot say this one in red is equal to the one in green because they have minus. One is positive, the other is negative. So I need to say cosine of 2 times 90 minus alpha is equal to minus cosine of 2 alpha. And this minus is the reason why you have minus here. Yeah? Look, you had plus here. When you move from here to here, I changed from plus to minus because I replaced cosine of 290 minus alpha with cosine of 2 alpha. That's why I did put a minus there. Okay?
So,
Yeah?
you know when you factored out the sigma x bar at top, isn't it supposed to be over 2?
This one?
No, the sigma x bar over 2. Yeah, that line. Isn't it supposed, when you factored it out?
Sigma xy. Do you mean this one?
No, it's the third line.
The third one. Okay, third one. Oh, you mean this one here?
Yeah, it's not supposed to be sigma bar x bar over 2.
Let me see. This comes from here. So you have So this 1 is because of this term. Sorry, because of this term. Oh, I know what you mean. Yeah, you're right. But it doesn't matter to the end because when you divide, this 2 is missing, right? Yeah, you're right. But when you divide these 2, they both cancel. Yeah, when you divide the 2 equations, so it does. At the end, it doesn't matter. But you're right. Yeah, the 2 was missing there. Thank you. Very good. So according to my calculations here, from this result here, I get an angle alpha equal to 54.74 degrees. Okay? So if you lay up your fibers with this 54.74 degrees in this direction, this is the optimal orientation. This can be something like, for example, instead of using, we are going to move to the laminate after the break, but instead of using, for example, if you don't lay up, imagine you put an angle here that is not 54, is, for example, 30, right? So when you put the pressure in the pressure vessel, this angle 30 will mean you will have some loading in the transverse direction to the fibers. And most probably it will fail, eventually, right? We are going to see, after the break, a failure, when we talk about the failure criteria, how we are going to assess that. But I think this example is very nice because basically it just explains you, in this example, we get the loading in the global coordinate system with its stress transformation here to get the stresses from the global or from global to the local or vice versa. And then we impose our optimal conditions, I would say, on the stresses in the local coordinate system to obtain this optimal angle, right? So let's do a break, 5 minutes. After the break, we are going to start laminate analysis. Okay, so let's do a break. 5 minutes, okay, so we come back at 10 past 10, so 7 minutes, all right? 10 past 10.